Welcome BCS members and friends to our BCS IBS seminar. Today we have a pleasure of hosting Professor Jonson from University of Gothenburg in Sweden. And the seminar today is a part of activities of Advanced Study Group on quantum functional mesoscopic weak links, whose convener is Professor Robert Schechter, and I asked Professor Schechter to introduce our speaker.
Thank you very much. It's my great pleasure to introduce Max Jonson, my friend and collaborator for more than 30 years now. Many of you know him because he is visiting regularly here as a member of Advanced Study Group. And he represents here also University of Gothenburg. He was educated in Gothenburg in Sweden and finished university at 1971 and defended his PhD at 1978. And since that, he was making postdoc in America and working basically after that permanently in Sweden, except a couple of more years. I mean, recently when he was working also in Scotland. So in 1993, he became a professor at Gothenburg University and have a very active scientific research activity, and which was actually very widely internationally recognized. And I can mention that he is a member of different kinds of committees and academies, including the Swedish Academy of Science and Korean Academy of Science and others. He is member of Nobel Committee in Physics and was a chairman of this Nobel Committee. And for 3 years, 2003, I suppose. His area of activity and interest is actually nanophysics in whole variety of phenomena which can be considered here. The dominating feature of this nanophysics is mesoscopics, as different kind of anomalous behavior on nanometer length scale. I can mention superconductivity on nanometer scale, magnetism, heat transport, electrical transport. Nanoelectromechanics was one of the active areas in his research. And very recently, he was focusing on superconducting spintronics. It's a new direction which tried to explore possibility to get superconducting magnetized and benefit from this magnetization which originates from superconducting condensate. So this is one of the result of his activity, magnetizing of BCS superconductor by spin-dependent tunneling. And I ask Mats to come.
Thank you very much, Robert. So I'd like to talk about the proposal of how to magnetize a superconductor by spin-dependent tunneling. And as was mentioned, this was work done within the Advanced Study Group that Robert convenes. And it's done together with Ora Entin-Wollman, Robert, and Anon Aharoni. They are all here. And I'm sure they can help me answer questions later on. There is a preprint uploaded to the archive. And the way we have worked, we have met several times here at the Center for Theoretical Physics of Complex Systems. And I'd like to take this opportunity to thank the director, Professor Flach, for providing such excellent facilities. It's always a pleasure to come here and being such a good host. And I also like to mention all the good help we have got from his staff in arranging travel and accommodation. It's a really well-run center, I think. All right. So let me say something about the motivation for this work. We all know that in electronics, it's what you want to do is you want to move and manipulate electrons and also the spins of electrons. Then we talk about spintronics. And in this context, people are quite interested in trying to use superconductors, because in superconductors you have dissipation-less transport, you don't lose energy. So there are many advantages. So that's okay with charge. But in conventional superconductors, the electrons are paired in spins, one spin up electron and one spin down electron. So there's no net spin. So in order to make spintronics with superconductors, you somehow need to magnetize them to create, say, spin triplet Cooper pairs with a net spin of 1. So, like I mentioned, in conventional BCS superconductors, the spins are locked into what we call the spin-singlet state. So the spin degree of freedom is sort of frozen out for the purpose of spintronics application. So the question now is, can the spin degree of freedom be unlocked to enable the spin as well as a charge degree of freedom to take advantage of the macroscopic phase coherence of the superconducting BCS state?
May I ask a question?
Yeah?
Could you please comment maybe on this topic and how it can be developed in D-wave superconductors when you have decay and ITC or something?
No, I'm not. I don't want to say anything about that. We'll just stick to conventional BCS superconductor for the purpose of this talk. It doesn't mean that there are not other ways you can create spins. This is a quite active area. This is the way I should turn it. So to discuss this, I would first like to comment on the difference between normal metals and superconductors when it comes to the electron excitations. So if we think of normal metals at 0 temperature, say, we have a Fermi energy. So below the Fermi energy in the ground state, all the electron states are occupied, and above the Fermi energy, no electron states are occupied. Then you can have excitations. You can have a lack of electrons below the Fermi energy. We call them hole excitations. Or you can have filled electron states above the Fermi. We call them electron excitations. And there's an electron-hole symmetry here, so that the energy of the electron excitation is minus the energy of the hole excitation. And creating an electron state corresponds to destroying a hole state, and the other way around. So in a superconductor, and we're all the time talking about the simple BCS type superconductors, we have different type of excitations. We have electron-like and hole-like excitations. So instead of this electron creator, we have this Bogoliubov creation operator, which I call gamma plus, and hole-like excitations. So instead of creating a hole, we have this gamma. And this is this Bogoliubov transformation. So an electron-like state is a combination of electron and hole states. And the hole-like excitation is similarly a combination. Sorry?
Star missing on the UK on the second line.
Yes,
Star on the U on the first line.
You mean this sign?
Yeah.
Should be plus?
UK shouldn't be complex conjugate.
No, I mean, I'm taking UK to be real.
Okay.
VK has to carry the phase vector. All right, and this is a conventional expression here. Big E of K is the excitation energy here. So here we have a picture, BCS. So we have Cooper pairs at the Fermi energy, and then we have excitations, and there is a gap to delta within which there are no excitations, and then we have here electron-like excitations and hole-like excitations. And again, there is an electron-hole symmetry, so the energy of the electron-like excitation is plus EK given here, and the energy of the whole excitation is minus EK.
What about the spin conducting?
It's difficult to hear. Can you?
What the relation of the spin conjugation rule is excitation. Your excitation is separated up and down, but two pair is total spin to zero. So
I cannot hear. I don't understand your question.
Do we have a microphone? Nothing. No. Maybe you can come closer here.
I capture it in your quasi-particle excitation is a spin in
This one?
gamma up and gamma down, but super pair is a total spin equals zero. So that excitation is always spin, total spin conjugate excitation, and up always gamma up and down has the same excitation, is the same population is the same.
I don't understand.
I think that these are the quasi-particles, not the super pair.
Yeah, this-
Refers to the quasi-particles.
But
Gamma are the operators, the quasi-particles, not the super pair.
they have spin, the particle excitations have spin. Cooper pairs are met, so there's no net spin. Okay. So let's now talk about the effect of a magnetic field. So if you have a superconductor, there's a weak magnetic field, which is different in different points of space. It means that no component of the electron spin is a good quantum number, and therefore a BCS superconductor is subject to quantum spin fluctuations. If you don't have the spin is not a good quantum number, it will fluctuate quantum mechanically. So this is bad for spin-singlet pairing of Cooper pairs. It suppresses conductivity, and if the magnetic field is strong enough, the superconductivity will disappear. So therefore, one must look closer at the question of pairing, how it occurs, must be reconsidered. For example, one has found that the critical temperature for superconducting alloys with paramagnetic impurities is reduced. So here is an old result of an old experimental work by Bert Matthias. I think it's from the late 1950s. And you can see here, he plots in this part here, the critical temperature as a function of the density of paramagnetic impurities. I think is gadolinium in this case. And you see clearly that there's a reduction of the critical temperature.
I'm sorry, one stupid question. What's the difference between paramagnetic impurity and the ferromagnetic impurity? What does it mean, the paramagnetic?
I suppose paramagnetic impurities can have magnetic field in different directions.
I see. In the experiment you have shown, the external magnetic field also applied in addition to the impurities.
No, I think it's just the magnetic moments from the impurities that has the
Magnetic
effect.
moment.
I don't think there is an
But the
external.
orientation random
Yeah.
in space.
Yeah.
Thanks.
Okay, let me go back to here. So now let's talk a little. No, I did that already. This is where I want to be. So now we will be interested in a superconducting system which is constrained in space. So there are bulk superconductor here, and there's a bulk superconductor here, and let's say there's a small connection here. So there's a constriction, and the characteristic size of this constriction, let's say that's D. The diameter here, say, and maybe also the length. It's a small length. And then another length is the coherence length of the bulk superconductor, psi c, which we will take to be large, so that the size of this constriction is much smaller than the length of the superconducting coherence length. Now, if you look at the BCS theory of superconductivity in a spatial representation, here is the Hamiltonian, is a BCS Hamiltonian. It has a trivial part here, so to speak, and then the part here which gives rise to superconductivity. So you see here there are two field operators. This one creates an electron will spin up at point R, and this one, an electron will spin down at point R. And here is the Hermitian conjugate to that. Now here, this is called the pair potential, delta R, or the gap function, because it turns out that will be related to the superconducting gap that is produced. That is given by a quantum average of two other field operators, psi spin up and psi spin down. So originally in the Hamiltonian, there are a product of four field operators, but you cannot solve that. So you have to make an approximation, and you do that by replacing these two by its quantum mechanical average. That leads to a mean field theory. And so this was studied a long time ago, of course, and Gorokov, for example, he put this, I mean, this is a self-consistent relation, right? I mean, delta appears here, and delta is defined here, and it's a function of the field operator. So this has to be solved self-consistent. And Gorokov formulated this way: delta is the integral, delta at R is an integral over R prime. There's a kernel, and this kernel has a certain range, and that range is given by the coherence length. So we see that if psi c is now very much larger than d, if we think of a point here, to want to calculate the gap potential here, you integrate over a large area here. So most of the contribution to this integral comes from points far away from the constriction, where there is no spatial dependence of the gap function. So therefore, that means that you can, when you write down to the theory for this, for the gap potential here, you can use the bulk value, which is obviously a great simplification. Now, let's say that this constriction also is a magnetic inhomogeneity. And let's suppose this magnetic inhomogeneity is due to the spin-orbit interaction, the interaction between the electron spin and its velocity, and which is a relativistic effect, and it creates an effective magnetic field. And let's say that this effective magnetic field goes into the screen here. So we have a localized effective magnetic field here. There's no magnetic field in the bulk parts here. Okay. So in the homogeneous parts here, the BCS superconducting condensates have electrons with well-defined spin projections along an axis, which we call the z-axis. So the spin is plus and minus h power over 2. That means that the SC is a good quantum number there, and you have this spin-singlet pair state. But at the constriction, spin is no longer a good quantum number, and that means that if an electron of a Cooper pair passes from one side to the other, there's a possibility that one of the spins of the Cooper pair will reflect. So the question here is, can these spin fluctuations here lead to the appearance of magnetization in the bulk superconductors due to the emergence of spin-polarized Cooper pair? That's the question we want to address. Okay, so I'm sort of saying this again here, a spin-orbit interaction here in this red part can rotate the spin of the thundering electrons around this effective magnetic field caused by the spin-orbit interaction. And the question is, can a spin cleave polarize Cooper pairs and magnetize a superconductor? So if we have a Cooper pair here with one spin up and one spin down electron, can what comes out on this side be a pair of electrons with spins in the same direction? That would be a spin triplet state.
How will the spin triplet state survive? Because it should break down.
I mean, that remains to be calculated, right? Of course, eventually there will be. I'm just asking, is this possible or not? And we'll see, maybe not, but then I wouldn't be here giving the talk. All right. So if we look at the probability for tunneling here, we will assume that is spin dependent. It can flip the spin. You can go from a state with momentum k, spin sigma, on one side to a state with momentum k prime and spin sigma prime on the other side. Okay. All right. So now to the mathematical formulation. So we use a tunnel Hamiltonian approach to describe the tunneling between two bulk superconductors through a spin orbit active micro-constriction. So we neglect any spatial inhomogeneity of the superconductors near that restriction, like I argued before. If the coherence length of the superconductor is much larger than the size of the constriction, then we can take this gap function to be constant. It could be different on the left side and the right side. And we use second-order perturbation theory in the tunneling amplitude T to calculate this. So here's a Hamiltonian, and this is the superconducting part. Here I use a Bogoliubov operator and the quasi-particle excitation energy. And here is the Bogoliubov operators. And then we have a tunneling Hamiltonian, which looks like this. So tunneling is not done by this quasi-particle, it's done by the pair electrons.
But what about H right?
Sorry?
H left is a region. What
The same.
H right is the same. I didn't write it. I use K for the left
No,
side.
I have
C for the right. I didn't write that down.
this.
So here we have one term in the tunnel Hamiltonian. So you destroy an electron on the right side, say, where I use P signal prime. And as you create an electron on the left side with possibly different spin, momentum K and so on. And this is a complex conjugate to that. So to solve this problem is straightforward but tedious, as I say. What we want to evaluate is the magnetization, let's say on the left side. So this is something that gives a dimension, and here is this quantum average. This is, if you look at this, you realize this will be the magnetization. So now, what can happen here? Well, we have two types of double tunneling event. We do second order perturbation theory, so we have two tunneling events to consider. And there are two different types that can create a spin triplet Cooper pair. So let's consider a Cooper pair in a spin singlet state in the left superconductor. So there's a probability that one of these electrons tunnels to the right superconductor, and then it tunnels back. And either going this way or that way, there's a possibility it will flip its spin. And if it does, we create the spin triplet state. And the other possibility is that both the electrons of a spin singlet Cooper pair tunnels, first one and then the other. And if one of them flips its spin in this process, then we would create a spin triplet Cooper pair. Okay, now, so let's see what this will lead to. So the Cooper pair electrons, they tunnel one by one. So it's real electrons that tunnel. So after the first electron tunnels, we are in an intermediate state. So first, let's say one electron tunnels, and since it has not another electron to pair with, you have to write to a quasi, you have to fill the quasi-particle states on the right. So after the first tunneling event, there will be one quasi-particle state to the right, and the other one was left alone can no longer pair either. So that will also have to go to a quasi-particle state. So there are now four possibilities. Both of these states can be quasi-electron states, so we call that the electron-electron channel. Or both of them can be quasi-hole states, so we call that the hole-hole channel. Or the state to the left could be a quasi-electron state, and the state to the right could be a quasi-hole state, or the other way around, the state to the left could be a quasi-hole state, and the state to the right could be a quasi-electron state.
Ahmed, why can't the Cooper pair tunnel as a whole? Why do you exclude this? Well, it can, right? Or you just don't care because it's...
Well, electrons, the real particles are electrons, they are the ones that tunnel. If you look at the
No, but you
tunnel
say
number two,
Don't live in the channel.
tunnel one by one. So I'm just asking, is there also a process when a Cooper pair can tunnel as a Cooper pair? Yes or no? Probably it's not interesting because nothing happens, right?
You have tunnel Hamiltonian in terms of bare electrons.
Right.
So you have to kill bare electron on one side and create a bare electron on another side. It's not enough. This single process is not enough to transfer two electrons.
No.
But if you introduce,
So you need to apply this tunnel Hamiltonian twice. So in perturbation picture, it goes like you expanded in perturbation theory, and you have one after another tunneling of electrons. Then each electron in superconductivity is superposition of electron and hole. So it's two-channel tunneling. Tunneling of electron is actually tunneling of either hole or electron with amplitude of probability. And this four combination is a picture how you tunnel one bare electron.
My question is just whether you can also consider a weak link to which nevertheless the whole pair will come.
The Hamiltonian of the link has
You will
to
have
contain.
you have this interaction term.
If you're interested, how microscope, no, we can discuss it.
Okay. Sorry, one question. You explained the particle hole symmetry, and from this symmetry, the process left and the right are the same. If you think that creating the electron among the gap is the same as the annihilating the hole in the negative energy, right?
I'm not sure I understand the question. Are you asking why?
The first, the upper two, for example, the processes.
By the way, this should be a P. Sorry, this should be a P.
You're talking about what will be then if you sum up over all these processes.
No, my question is that the first upper two processes, left and the right.
This one you mean?
No, the left one and the right one.
This two?
Yeah.
Why are these the same, you're saying? Why is this EK and this is minus EK? That's your question?
No, these two are the redundant process, or these two are distinguishable?
No, these are different processes.
Yeah, different. You mean the different, but if you apply the particle symmetry to this left figure.
Yeah, but in life you don't. Particle hole symmetry is a theoretical concept.
Yes.
In life, you have this process and that process, and they're different. They're different quantum states.
That's why spin.
Okay, so when you do this perturbation expansion, you will find four different terms which I've illustrated here. There are sums over K and sums over P, of course. And we know that the intermediate states, the energy of the intermediate state appears downstairs, right? So here you will have 1 over EK plus EP. And here you would have 1 over minus EK minus EP. So they cancel. And same here, here would you have 1 over EK minus EP. And here you would have 1 over minus EK plus EP. So they cancel. So these are probability amplitudes. And in quantum mechanical language, you say that you have interference between these different channels. And in this case, they all cancel. So there's no result. All right. Now, let's apply a bias voltage between the superconductors. Now, if you look at the electron-electron channel, first electron tunnels, and let's say real electron gains energy EV when it tunnels because there is an electric field in the constriction. It means that the quasi-particle state has to have an extra energy EV to accommodate this. And same here, in this whole channel, the quasi-electron hole energy will have to be increased by EV. So now we see that the destructive interference is listed because now the energy dominator in the intermediate state will be here, it will be EK plus EP plus EV. Here it will be minus EK minus EP plus EV. So that's different from 0. It will be proportional to voltage. Okay, so that means that there will be a result now. And so I mentioned there are 2 types of spin flip tunneling processes that gives rise to magnetization. So here I talk about the first type. Let's call that spin flip reflection of 1 electron. So 1 electron tunnels from left to right, and then tunnels back, reform the Cooper pairs. And there can be a spin flip. If so, it contributes to the magnetization. So it's proportional to V here, because we needed a bias voltage to break the destructive interference. And we see a prefactor here, which is the energy gap in the left squared.
If you apply bias voltage, so you have, I see Josephson effect, so phase also changes. Superconductor.
The what changes?
Phases.
Phase changes, absolutely. But in this case, you go from the left to the right, you pick up a factor e to the IEVT, you go back, you pick up a factor e to the minus IEVT, so they cancel.
Sorry, if we apply voltage, you have time-dependent problem.
Yes.
Yeah. So
let me say like this. There are 2 types of processes which are relevant here. One type we are talking about is you transfer 2 electrons from the left lead to the right lead. They transfer Cooper pair. This process depends on phase difference and will depend on time and so on. It will come later.
We'll come on the next slide. Okay.
The first process is like this. We don't transfer Cooper pairs. There is no current produced by this. You just take Cooper pair, take 1 electron from Cooper pair. It goes back and forth, keeping the Cooper pair on the same place, untouched. So this doesn't produce any current. It doesn't extra Cooper pair tunnel. It doesn't depend on phase. And this doesn't depend on phase.
Okay, so we can note here that the right electrode doesn't have to be a superconductor because delta R doesn't appear here. That's one observation. And the result here, there's an energy denominator, there's integrals over energies and so on, and then there is a factor that depends on the spin flip mechanism. So far, I haven't specified that. Now, one can make an example to see that you do get something which is finite. You have, though, to apply an external magnetic field in this case to break time reversal symmetry. Okay. So now we come to this other case. We have a spin flip transmission of a Cooper pair, which injects a spin triplet pair with finite magnetic moment. And that leads to a time-dependent AC Josephson-like magnetization, like you were anticipating, I think, Ronja. So again, for the left superconductor, again, it's proportional to the bias voltage here. And now we have a product of the two gap functions in the left and in the right, which could possibly be different. So we see that both sides have to be superconducting for this to be finite. And again, there is some expression here that involves energies and the pre-factor, and then something that depends on the specific mechanism for spin flip. And so here, the first electron picks up a phase e to the I EVT. Next one also picks up the phase e to the I EVT. So therefore, you have, it turns out to be a sine 2 EVT, and this is the phase difference between the left and right superconducting condensates.
I'm questioning. So, size of gateways in triplet pair and spin-singlet pair is the same.
I'm sorry,
The size of the gap for the spin-singlet and spin.
Sorry?
The size of the gap for the spin-singlet and spin-triplet.
Oh,
It's
are they the
only
same?
for the singlet.
That was a question.
yeah, okay. No, it will be.
It is a perturbation calculation around the BCS.
Yeah,
You can see the BCS superconductor singlet, spin neutral, no G wave, no nothing like this.
all right. So what can we conclude from this work? Magnetization of a BCS superconductor can be induced and controlled by electrical means because we have this bias move. And this magnetization can be localized on a nanometer scale. Of course, we have this tunnel Hamiltonian model. We cannot describe the spatial distribution of the magnetization, but we anticipate that the magnetization will be very close to the constriction. So small scale. And the constriction would act like a point-like source of a spin current. It can be activated electronically. Okay, now what can we possibly do in the future? So the magnetization we have talked about is a ground state property of the superconductor and could possibly be used for quantum information processing. So what we are discussing now, what we might want to look at is to replace one of these bulk superconductors by a small superconducting grain. So that's often called a Cooper pair box. And here is the other superconductor. And as before, we have this magnetic spin orbit active constriction here. So the difference now is that because this is small, when you add charge to this small grain, you have to pay an electrostatic energy. So one can have Coulomb blockade or tunneling and so on. Now one can affect these things by a gate here, a gate voltage that will produce an electric field fed by the electrons here. So you can, for example, create a state where the state with n Cooper pairs and n+1 Cooper pairs have the same energy. And that means that there will be quantum fluctuations between these two states. And at the same time, you could have a quantum fluctuation of the state between states with no spin triplet state, so that would be spin 0, and one spin triplet state, spin 1. So, we would like to see if one could use this for or something, some spin charge quantum operation may become possible, perhaps transduction between spin and charge in the qubit. But this is all speculation at that point. At this point, and I would just end by saying thanks to my collaborators, Robert again, and Amnon and Dora, who are all here, and also thanks to our host here at this center. Thank you very much.
Thank you very much. And now it's option for lots of questions. Yes.
Question. So, can you come back to slide with magnetization?
Slide with magnetization. Let me see. Push here. Sorry.
Yeah. For example, yeah.
This one, you mean?
Yeah. So basically, I suspect that the result that you get here come from your perturbation theory with the tunneling, and the RQ and RN here, RQ and RN.
Okay, so Rn is the resistance of the constriction in the normal state.
Yeah.
And RQ is the quantum resistance. I didn't define it. It's h bar over e squared.
And then is this like appear in the T K prime that you have in your perturbation theory, right?
Well, I mean, this Rn here is proportional to 1 over the tunnel amplitude squared.
So
I mean, without any.
So my question is, what is how do you derive the T K prime sigma prime in the microscopic picture?
How I choose the transmission amplitude, you mean?
Yeah, in the microscopic.
Well, I mean, there's one part which is sort of the trivial part, which doesn't have any spin flip part. And I don't say anything about that. I put that into the resistance for that's the same that appears in the resistance in the normal state.
Yeah.
So
This is transmission without spin.
experiment.
Yeah.
But then there is a spin-dependent part, and there are various models for that, and we use a particular model to get this result.
But I guess this comes from the transmission.
Yes,
Operator.
transmission amplitude.
Yeah, and my question is like, you have like detailed derivation, detailed microscopic derivation of this transmission and come up with this result?
What I'm saying is that I'm not doing it. So
It's here.
You show the Hamiltonian.
It's in this.
I showed the Hamiltonian.
It's in this, what you
Okay,
asked
we can look at the
is in this.
Hamiltonian.
I think the question is the relation between the T, K prime, sigma prime,
Yes.
and the W.
Yeah. Okay.
So didn't I? Okay, I missed it. Where do we have it from?
Up here.
No.
No, one more.
Here.
Okay, I didn't. Here.
Here,
Okay,
yes.
yeah. So this T here, I assume that there's no. Well, the T here has one sort of trivial factor and one non-trivial factor, which describes the spin-orbit interaction in our case.
Yeah.
The non-trivial factor, I don't say anything about. I express it in terms of the normal resistance of the junction,
okay.
and I can take that from experiment.
Okay.
And then for the spin-dependent part, we use, certain
Models.
Yeah,
So I calculate the W model.
Yeah.
So you formulate this in W.
Yeah, I'm not sure I wrote down that. Let me see.
Yeah.
This
The W divided by Rn is basically the T squared from the perturbation
Yeah.
theory.
TT star.
More questions?
So the spin flip happens during the tunneling.
Yeah.
Right. Now suppose you get this triplet here. What's then in the bulk of the left or the right compartment, the mechanism of it relaxing back down into a single? Because you said it only exists close.
Well,
to
the direction of the spins in the bulk is defined by the pairing potential, and it gives a direction which we call Z direction. That's all. And then this is a coherent system, so that's presumably why the spin triplets have a spin in the same direction too, because otherwise you could think that each spin triplet may have an arbitrary direction of its net spin, but that doesn't happen since we have a net result. And that must have to do with the coherence of the system.
And your question that you described the two processes.
Yeah.
This the magnetization, one the back and forth, and just the tunnel of the two.
Yeah.
Can we compare the some order of the magnitude of the two processes? That if you did experiment, which process larger than the other?
Yeah. Well, this process is larger. We have two factors of magnetic field here. We have this factor, and then we have something which is of order 1 here. I should press this one. Now the other processes also have delta squared and this factor, which is the same. But you see this, because you have to break time reversal symmetry. In this case, you have an additional small factor of an external magnetic field over the Fermi energy, which is small. And then the rest is order 1.
But regarding the some time domain, the second process, the later one, there's some oscillation in time. So if you do this, the effective average in time, then
average in time is 0.
0.
Yeah.
Okay, I'm just talking about the amplitude.
I see.
But the point is that if you have time-dependent magnetic moment,
Yes.
and you have covered by ferromagnetic layer, for example, this oscillation creates spin waves. It generates spin wave, which can be detected. So this is a way how you can do it. But also you can use this static magnetization for qubit manipulation with the spin of triplet pair.
Yes, that's a question.
Sorry, quite my question. So in BCS superconductors, you can have Meissner effects. Right?
Yes, Meissner
so
effect.
This thing that you just mentioned, that this magnetization is really it's close to the constriction. So will that decay be like exponential, like in Meissner effect, or how do you expect it to be?
You want to speculate on how the magnetization decays away from the constriction, possibly due to the Meissner effect. No.
It's due to injection of magnetization from the surface, and surface is point-like contact. So this spread out three-dimensionally, and 1/r squared, will decay. This
geometrical dilution.
Geometrical spreading.
And then the
of proximity effect.
Magnetic effects in our case occurs only in the constriction. No, we don't have a magnetic field in the superconductor, so we don't worry about the Meissner effect.
And also because in your model, you don't really include the information of how wide this constriction is. You just said that this D
the model is one-dimensional,
right.
I say, but we know from other problems about this geometrical dilution effects. So we would expect that to happen the same way.
So the way to consider your effect is consider this model, calculate spin current, for example, which carries through this point contact, then go to three-dimensional lead and say that you have point-like source of the current on this lead, and see how this point-like source will inject current in three-dimensional. And intensity of this source will be already calculated in this model. So this is how you solve external part of the problem.
Which we haven't done, just
Haven't done that, but it can be completed with it. But qualitatively, it's like this. Foreign electrons, foreign Cooper pairs, which just tunnel, are spread in space, I mean, three-dimensionally. A number of Cooper pair conserved, so it's 1 over r squared. The flux should be conserved. It's approximately should go like 1 over r squared, with some details of angle, maybe distribution. I mean, this angle.
I thought Sergei was asking a different question. Don't these triplet pairs decay in this BCS superconductor because they have no reason to survive there? And we haven't thought about that.
It's not decay. It's not lifetime. It's spreading in space.
Yeah, but that's on top. But this is a different
What do you mean
question.
by spreading it? I mean, if you continue this process and there's no way to kill them, you will just magnetize the entire sample. If you wait long enough. I mean, that's
The time sample is very, very large.
well, you just wait long.
It's interesting, Sergei, we consider not current, but we consider magnetization. And we found that magnetization is oscillating in time, so it's not accumulated. Its average is 0. And then permanent, constant. Again, doesn't increase in time, but it's constant. It's like proximity effect is established and stay time independent magnetization. Just in space, it's distributed like 1 over step. This is one of the important points that we get static magnetization here. Static. It means that spin current is 0 because spin current is time derivative of the static magnetization. So spin current doesn't flow. But we have static magnetization in ferromagnetic, which can be used in equilibrium properties like storing information and manipulation of the information. It's equilibrium phenomenon.
But sorry, static or oscillate?
Two parts. There are 2 parts.
There are static and oscillate.
yeah. This is a step.
But you can have only also static. If one of the superconductor is normal, not superconductor, this oscillating current, Josephson current disappears, and we're left only with static magnetization. If one of the leads is normal.
But I think that the field induced by this the magnetization
Sorry?
negligible. The field, magnetic field induced by this magnetization is negligible.
It depends if you want to work with this magnetic. If you want information of what we're doing when we're considering spin qubit, we're talking about one spin contribution. And this is exactly spin triplet Cooper pair contribution. So you need to consider small dot.
Yeah.
Small dot. Cooper pair box. And then
You are correct, it's a small effect in what I'm talking about. Now we are speculating about going further and consider this Cooper pair box instead. And just like Robert says, here you have states with, say, 0 and 1 spin, and that only doesn't present that problem.
Proximity effect is okay. The normal metal together with the superconductor, and then the superconductor kind of flows into the normal metal and stays there.
Yes. Yes.
Just to bring analogy, we are talking about charge qubit. What is charge qubit? One single Cooper pair, 2e, only 2e, is delocalized between 2 conductors and going back and forth. And this effect of only 2e on this charging dot by 2e is noticeable important for computation. Now we are talking that this Cooper pair is triplet. And then it's going back and forth. It carries also magnetization. So your spin is fluctuating on you. And this single Cooper pair spin fluctuating. It's a spin qubit. So, and we have in one dots, we have both charge and spin qubit. So it's would be spin charge transaction between qubits arranged by this dot, because both spin and charge qubits are in one dot.
We speculate at this point.
Yeah, we speculate. It's stuff for the future.
Yes?
One more question. So earlier you showed an experiment with this paramagnetic impurities. Because you finally conclude that this constriction can just be thought of as single point. Can you use this formalism to explain the earlier experimental data that you showed? With multiple constrictions and so on?
I didn't quite understand the question. You're talking about paramagnetic impurities,
Yes.
and then
So because
we could describe that too. Then we would have to have a different model for the transition.
right. What I was thinking is that if you have a network of these bulk superconductors,
Yeah.
which are connected by these
Okay.
constrictions, and then can you speculate that this formalism can explain that experimental data?
What experiment did you do?
The ones you showed before.
The one I showed before.
Yeah, with the paramagnetic impurity.
I think the question is that whether this the link can change the temperature.
It's impurity.
I see.
You don't need this constriction.
If
No,
you
I
make
think-
multiple constriction, then these
In that
constriction
experiment, I think it
affects
was
the-
one bulk sample that contained.
Yeah, but what he says is that if your constriction, as you said, is a point-like thing,
Yeah,
then
okay.
maybe you can just forget about constriction and say you have an impurity.
Oh, I
And
see.
now you
Okay.
have some
I
BCS
see, okay.
condensate which interacts with this or somehow with this impurity. And
I
then
don't
maybe
know.
you
That
can,
experiment was already explained by Gorkov, but I didn't.
but maybe it was the wrong way. But not.
It's impurity, we should be very careful, because impurity is additional degree of freedom. If it is random, if this different impurity fluctuate independently, they will destroy all this phase coherent phenomena. Impurity should be frozen and act as a field, not as a degree of freedom, but external field. Then it will work.
I'm not sure. Because you want the spin of the electron that was not magnetized before, this spin I am not sure that single magnetic impurity in
It's an interesting problem to consider and see what will happen. It's just speculation.
Isn't it wonderful that the more questions you answer, the more questions? That's the whole idea.
So more questions? I think it was a lot. And if somebody, because of hearing problem, was not heard, maybe we'll after seminar meet and clarify these questions. I mean, so we should thank again.